much, and I want to thank the organizers for making this event and inviting me. It's a special pleasure and honor, really. And before starting my talk, I want to tell about my first meeting with Emmanuel. And actually, we met before, but very briefly. But there was this time during COVID that two groups were proving basically the same theorem with very different tools. And what could have been a competition actually became very friendly and exclusive, inclusive meeting. I mean, we organized. It was COVID time. It was very in fashion to organize a Zoom seminar with Greg and Emmanuel on one side, and myself and co-authors on the other side. I think everyone, and also others, and everyone was learning new things. I think it was not balanced, it was not fair, because for me to learn the O minimality and I don't know, variation of odd structure was very, very hard. For Emmanuel to learn the basics of ergodic theory was very easy. It was so, but I want to thank you for that and for the attitude towards mathematics that is very inspiring. And and this old work was about rank 1 lattices, and today I'm going to speak about higher rank lattices. So this is different topics. I will not start a new lecture at the very last minutes of my talk. I will speak about this work about higher property T and Banach representations, and I'm very proud to present the co-authors. So this is joint with a couple of very talented young mathematicians, and also Roman Sauer, very talented older mathematician. And so this is also a special pleasure to speak about this topic. And I will start with being old enough I can use this word, philosophy. Higher rank lattices are rigid. This is behind my talk. So we've seen several times the definition of a lattice, but nonetheless I will repeat it. So this discrete gamma in G of finite covolume. So this covers this. So for us, G is most of the time simple Lie group. So it's a topological group. Most of the time it will be a simple Lie group. Sometimes it will be periodic Lie group. Simple Lie group. The rank is dimension of maximal split torus. Higher rank means that it is 2 or higher. And example, as always, is SLNZ inside SLNR. So I explain this. I should explain what I mean by rigid. So example of rigidity, for example, property T. Most of us know what it is. I will give the definition nonetheless in a few minutes. This is analytic rigidity. Another example is property FA. It is called fixed point property. For actions on tree. This is geometric rigidity property. So this is called FA sometimes. So this is a general philosophy, but today's theme is the following. The higher the rank is, the more rigid the lattices are. So examples that will kind of carry our narrative is higher property T and higher fixed point properties. And I want to explain some about the relation between these two properties, etc.
Sorry, can you recall what property T is?
Yes, I will recall what property T is, yes. So this is just to give you an idea of what are the subjects I'm about to talk about. And I will definitely will explain this, which is less known, and what I mean by these properties and objects. But the setup that will lead me really is a cohomology theory, and in particular a continuous cohomology for my groups gamma and G. So let me recall this. I mean, I think this is well known, but maybe not as well known as it should be. So let me give some basic definitions. So this is a theory that was developed by Mosto and Hochschild in the 60s. I mean, people used continuous cohomology, but in not very organized fashion already in the 50s. But while the algebraic theory of cohomology of groups and spaces was well developed using more and more sophisticated algebraic tools, homological algebra, the theory of continuous cohomology of locally compact groups suffered somehow the problem that it was not well defined in algebraic sense, because mainly if you just look at locally compact coefficients, you don't have enough injectives, enough projectives, so you have to modify the theory. And also the theory of topological vector spaces, the category is not a Abelian category. When you have two Banach spaces and I have a map between those Banach spaces, so the thing is, again, locally compact spaces are not enough. I need to enlarge my point of view. I need to consider Banach spaces and also inverse limits of Banach spaces. These are Fréchet spaces typically. And when I have maps between those, the image need not be closed. So I don't have natural co-kernel in the category. So there are kind of obstacles to overcome. Nevertheless, a theory was developed, and here it is. So G here is topological group, typically locally compact group. And it acts on V. This could be a topological vector space, but let's say that it is a Banach space. And then I have the bar resolution. I can have other resolution as well, but this one is easy to write and consider. So these are continuous functions from G to V. And I have this map. I'm taking here the non-homogeneous. Bar resolution. And I have another map. I will not write it down. And more. And these guys here, what I want to emphasize, these are Frechet spaces. Because I didn't specify any boundedness condition on those objects. And what I want to study is resolution by Frechet spaces, which are injective in a certain sense, which I will not define, but what it gives me is not only cohomology. Maybe I'll write down first that it does give me cohomology, and then I'll say some words.
Sorry, what is G squared? What is the notation?
Sorry?
G squared, is that just a product? Or?
Yeah, just a product.
You may confuse some formulas because you wrote it as if it's a resolution, that is, the map is injective. Since you wrote V minus GV, since V minus GV, it means that if the action is trivial, you get 0. So probably you just want, I mean, it is not, you probably want just G going to GV, I mean, just.
If the action is trivial, I want to take, I want that H0 will be V itself.
The bar resolution, do you claim this is a resolution of V?
This is a resolution of V, yes.
But the first map is not injective.
So I'm saying it's not really that this is a resolution, and this is a chain complex that I use to define the cohomology. So this is, I don't want to give I don't give a full course on relatively injective resolutions. So I'm using this as in an ad hoc manner, really, to make the following definition. So this gives the continuous cohomology so HIGV is, by definition, I will not introduce the notation, it's clear, the co-cycles of the ith term modulo the co-boundaries, so the kernels modulo the image. So take this as a definition. What I want to emphasize is that I can make it somehow independent, in a certain sense, of the actual resolution I use. This not only, sometimes people use C here, I will just omit this because I will forget anyway for continuous. This is not just an algebraic space, vector space. It also carries a quotient cohomology, a quotient topology. This is a topological vector space. In fact, what I can do always is to map. So this co-cycle space is a kernel of an operator between Frechet spaces. This is a Frechet space by itself. It's closed. This one is not closed, as I hinted before. And I can always take its closure. And what I get is some sort of Hausdorfification of this object, which people denote H bar. So this is a Frechet space by itself. And also here you have semi-norms but they don't separate all points. They don't separate 0 from other points, and this is exactly what I fixed when took the closure here, took this quotient. And maybe I should also say that this is typically a Banach space. When I say typically, I don't mean this is a Banach space for the general group, but it is a Banach space for the general group that we care for. For example, if G was a discrete group, this will be a Banach space if G, I should say gamma when I think of discrete groups, that's how my mind works, if gamma has finiteness properties. And this also should be the case for locally compact groups if they have appropriate finiteness properties. This is somehow not well-established topic, and we don't know for sure what happens, but this is how the picture should behave. This is the picture I want to convey, and now because we deal here with Fréchet spaces and continuous maps between those, a general tool that we have is the open mapping theorem. Which basically says that the image of a map is closed if and only if every element which is almost in the kernel is closed to an element in the kernel. In our situation, Hi is Hausdorff. If every almost cocycle is close to a cocycle. And if every I cocycle is closed I minus 1, yes. Correct. Okay, and now I can look at the map V to CGV that I'm looking at, I wrote there, and ask myself what is an almost cocycle in this setup. And this is why I was very explicit in writing these maps. G goes to V minus GV. And here comes the definition of property T. This is by Kashdan. I'll say aloud Kashdan's original definition. He said that every almost invariant vector in V, every vector little v, such that its image is almost 0, is closed to an actual invariant vectors. But by this open mapping theorem, this is equivalent to the formulation I'm giving now, H1 GV. Sorry, I should have said this before, every unitary representation, so this is unirep from now on, G. So V here, this is a Hilbert space. H1 GV is Hausdorff. So this is not how Kashdan wrote his definition in the first place. This is a reformulation by Guichardet, who studied continuous cohomology. I said that Morstow and Hochschild were the ones to develop the theory initially, but it was followed by many others. And Guichardet gave a lot of did a lot of work on this. And now, after this, there was a theorem by Guichardet and Delorme, which I still find, I know it well, but I still find it very, very surprising. T, if and only if, for every unirep H1 GV is 0. So of course, if H1 GV is 0, then the cohomology is reduced. But this is not if and only if for any specific representation. But if you quantify over all unitary representation, this becomes if and only if. That's a breakthrough by Delorme, and hence we have this cohomological vanishing interpretation of property T, which for me is the easiest to remember. So a group has property T if for every unitary representation H1 vanishes. You're satisfied? Excellent. So again, but this equivalent is non-trivial, and somehow it breaks if I change the setup by a little. For example, if I consider not first cohomology, but higher cohomology, or if I don't consider unitary representation, but a more general class of representations. So this particular theorem completely breaks. And this is part of what I want to emphasize today.
But just a quick question then. But the Hausdorff condition would still hold for the higher or different types of representations, or for... So
what do you mean by this? The Hausdorff property is the Hausdorff requirement is a property of G, if it holds for.
Right, but I'm asking, would it be automatic that once you know this is Hausdorff, that it would also be a Hausdorff?
Yeah, I mean the zero space is Hausdorff. Zero implies Hausdorff. Zero.
But I'm saying that the Hausdorff condition. If you know property T, do you automatically get Hausdorff for the higher cohomology? No. No. That's good. Thank you.
Or maybe.
You have to assume some minor hypothesis. That's for the Fauchet topology, like the G is locally compact.
Yeah, so I didn't write it down precisely. My topological group are assumed to be locally compact and second countable. Most of the time, there will be G will be a Lie group, and gamma will be a discrete group, a countable one. But yes. Right, where am I? So maybe just a few facts. So just to relate, I already wrote this, but let me emphasize this theorem by Kashdan. Basically by Kashdan, higher rank groups and lattices have T. And another theorem by Watatani, T implies Fa. I write it in this shorthand notation. Let me just say it again. If a group has property T, every action on a tree of it has a fixed point. Now, this theorem also already implies something non-trivial, maybe. Rank 1 p-adic group do not have T. They act on the Brouatitz tree without a fixed point, so they never have property T. for rank 1 Lie groups, the picture is more complicated. So there are 4 classes of simple Lie groups of rank 1, SON1, SUN1, SPN1, and F4. And SON1 and SUN1 do not have property T. SPN1 and F4 do have property T in the sense that I wrote, but not in stronger senses that I will explain in a few minutes. But really, the theory for p-adic groups is somehow maybe simple in a misleading fashion. So maybe I'll, towards giving generalization towards higher property T, let me now describe higher cohomology of simple p-adic groups. So let me assume higher rank. So in rank 1, we somehow understand everything. We don't expect any vanishing of cohomology. They act on the tree, so the cohomological dimension of those objects of simple Lie groups, simple p-adic groups of rank 1, the cohomological dimension is 1. So no higher cohomology theory. Now gamma is a lattice in such. And take a unitary representation. What happens is that we have vanishing below the rank. So this is an example of higher property T that I will give in a minute. At the rank, might not be vanished, might not vanish, but it is always reduced, always Hausdorff. And above the rank, you again have vanishing by what I said earlier, basically, by cohomological dimension. The Brotitz building as a dimension of the rank of the group. So you don't have and it is a contractible space on which the group acts. So you don't expect cohomologies over this dimension, not only for unitary, but for arbitrary coefficients. Yes?
Sorry, so for p-adic groups, is that just a closed subgroup JL and QP? Or is it more?
Yeah, simple ones, I assume, yes.
Okay. But when you look at representation, it's still in real Hilbert spaces?
Yes, the representation theory I'm considering now is real Hilbert spaces. Yes. So, yeah.
And it's important unitary, so for
it's important this is unitary, yes.
For Banach, it doesn't necessarily.
So for Banach, it depends on the space, and I will come back to it. The picture, okay, for p-adic groups, the picture should be very similar for a more general class of Banach spaces. For Lie groups, again, the picture is more complicated. I'll try to describe it. Now, a simple Lie group. Let me try to explain. And gamma lattice. let me try to give an analogous picture. So again, HK gamma or V or G is 0 for below the rank.
That's a real Lie group?
Sorry? Yes, this is real. I use Lie for. Yeah. Okay, I guess I use it in different meanings, different times. Still housed of other rank. Might not vanish. But really this depends on G. So for some groups G, like SPN1 that I mentioned earlier, the vanishing of cohomology rank is higher than the split rank. And this is a very interesting story going on here. And then, unlike the p-adic groups where the cohomological dimension is the rank, the cohomological dimension of a simple Lie group is the dimension of the symmetric space. So it's not, it's somewhat quadratic at the rank typically. And then there is a huge range that we don't understand entirely what's going on. There is Poincare duality. So when you get closer to the cohomological dimension, again there is a vanishing phenomena, but over the rank, basically the picture is complicated. And maybe I should add an interesting.
Excuse me, you make no assumption on V, it can be arbitrarily large?
V could be arbitrarily large, yes. This is a unitary representation.
Hilbert space.
Yes.
Yeah.
This is gamma, go to UV, unirep, arbitrarily large. Yes. And this is a result with Roman Sauer that we had recently. And maybe it's time now to define the higher property T. I think you are guessing the definition. Where is the eraser? Must be here somewhere. Aha. So gamma has Tn if for every unirep. Maybe I forgot a very what I wrote is incorrect as I wrote it because I should have started before putting this board. Before writing this, I should have given a counterexample. I'll give the counterexample, then I'll make corrections, and then I'll give definition. Sorry for that.
Yeah, you already mentioned that T fails for some SUN1 and SUN1, which contradicts this.
Let me give the following example. HK of SLNZ with trivial coefficients, I claim that it is the same as SLNR trivial coefficient. This is below the rank. This is, again, this is not a trivial statement. This follows from my work with Roman Sauer. But this one is well understood. This is the space cohomology of the symmetric, of the dual symmetric space. That's SUN1, SUN mod SON. And the cohomology of this space is well understood. And this does not vanish for k 5, 9, 13, and large enough. So the cohomology stabilizes, and it goes by, I mean, for k's which are, I don't know, 4i plus 1, the cohomology here does not vanish, and hence this does not vanish. And what I wrote here cannot be correct. I'm sorry about that. I'll put in the shadow, I'll put the extra the extra assumption that we have. Do you see this? We don't have invariance. So I'm excluding this thing here, which I know that not to be in line with what is written there. So the periodic picture, which is fairly simple, is somehow misleading. And if I want to come up with a higher property T, which, according to our philosophy, should be applied to higher rank lattices in simple Lie groups, I should make a corrected definition, which now I will state. I will assume that there are no invariants, and I will demand vanishing for every k less than n. Okay, that's my definition of higher property T. Any questions so far?
N is your rank now? Oh no, oh, Tn.
Tn, yes, this is T sub n. Let me put parentheses here. This is a property depending on n. Sorry?
What could be gamma? It's a pretty
So the theorem is for lattices, I'm rephrasing this, in simple Lie group have T rank minus 1. Did I answer?
no, it's just in your definition. Gamma can be any. What is gamma?
Gamma is gamma is a locally compact second countable group.
Okay, no,
because I didn't use G.
We think it's a lattice, so it's right.
Yes, you're right. This also goes for G. Fair enough. Okay. Now I introduced continuous cohomology for arbitrary Banach space. I then discussed unitary representation, and there's so much more I can tell and explain about unitary representation. There is a beautiful theory over here that what I explained here is just a bit, but I want to move now to more general Banach spaces. So this is my work with Fuhrmann, Gelander, and Monod. We show that T is actually equivalent to the following. I can instead, so now I think of LP spaces. Unitary representation is L2 space, and I want to change P and look at representation into the isometry group of LPX, some Banach space of type LP. Then H1 gamma LPX is 0. So the statement here that if this works for 2, then it works for every p between 1 and 2. And also if it works for any p between 1 and 2, it works for all others, in particular 2, and you have property T. So this is a version. And also we proved, moreover, so this is for a general group with property T. For higher rank lattices, we have a stronger property.
Sorry, you said this theorem was a statement about any group again.
This is any group.
Gamma notation
Yeah.
again, but you didn't.
Yes. Yeah, I use the gamma notation again, but this is for any group. And now I think about higher rank lattices. So notation gamma is justified, and I'm saying that there is a vanishing for every p, not only in this range p less than 2. So this is so higher rank lattices are more rigid than the general group with property T. And indeed, Pansu had to go, I think, just he left, or I missed, yeah. But he showed, he should have waited. This is not the case. So the moreover part is not the case for rank 1 groups with T. So if you look at higher P's, then there is actually a difference. The T rank, or the vanishing of cohomology for unitary representation rank and the algebraic rank of a group are not the same usually, but if P is large enough, they are in a certain sense. This reveals the rank 1. Thank you. So SPN1 has this property. Where am I? What did I do? The piano. So LP spaces come up naturally in analysis, but if we are already mentioning Banach space coefficients, we can ask about the general theory of Banach spaces and the cohomology, and people do that. So X is what? X is any measure space.
No probability, just measure space.
No, yeah, any measure space. So for example, and this is a very important case, X could be gamma itself, and this could be little LP of gamma, the completion of the regular representation with respect to the Pinot. And Pansu, who had to leave, was studying this from geometric point of view, and he has very, very interesting result about it.
So Pansu's example was about LP gamma in here.
Sorry?
Pansu's example, this is not the case. It is about.
Pansu's example is yes. And I will come back to this. H1 gamma, LP gamma, not 0, P large enough. Yes.
And sorry, why is such a result to be expected? Is it expected to be a strong link between, like, why was this result expected?
Which result?
That property T implies that the isometries into LP have
I think I will come back to this, and maybe if I have the time, I explain philosophy. I see that I will not have as much time as I expected. I'm going slowly, but you can ask again later. So now a very recent breakthrough by Oppenheim. This is not the same Oppenheim that he was speaking about. This is Saar Oppenheim. This is my former student. Delat and De La Salle. They proved that actually this vanishing of H1 result for higher rank lattices and an isometric action on Banach space, and now I'll take here a class of super reflexive Banach spaces. So this is a class, a very general class of Banach spaces, including all LP, not including L1, but all LPs for P larger than 1. H1 gamma V is 0. So this was conjectured for a long while. Vincent Lafforgue proved it for p-adic lattices, and then very recently those guys were able to prove it for lattices in simple Lie groups. Now conjecture V super reflexive and no invariance implies vanishing below the rank. So the conjecture that is natural to make is that this higher rank property T definition that is over there for unitary representation could be extended for a larger class of Banach spaces. So what it should follow from whatever is it about the higher rank that makes it the higher rank lattices and groups that makes it tick, and the geometry of the Banach space. So super reflexive I will not define, but it includes all LP spaces for which are reflexive. Maybe I can say a word. You have reflexive Banach spaces. This is a natural class. We all know what it is. Double dual is itself. But this class is not stable under taking ultra limits, ultra powers, and the subclass that is stable under taking ultra powers. So that reflexivity is actually shown by some finiteness properties. This is a super reflexive. Super is really, in Banach space theory, is a property that is stable. Superclass is a class that is stable under taking ultra limits, basically. Now, the new result that I want to tell about today is the following. The conjecture is true for LPV for all P's in this range, including P equals 1, which is not part of the conjecture formally, and the P equals 1, maybe I should remark, the P equals 1 is harder somehow, and techniques should follow a work by myself, Gelander and Monod. So I mentioned earlier a result by Fuhrmann, Gelander and Monod about vanishing of cohomology with LP coefficients. This excluded P equals 1. It was harder, and then later we, by different type of techniques, we settled the P equals 1 thing. But whatever it is, what we do have today, and this is, let me reread it because this is the main theorem of today, is that
This LP.
yes, LPX, thank you. it's hard by the board. And also time moves differently here, right? You know this, you noticed. Because your talks went forever. Yeah. That was a joke of Benson Farb, which I shouldn't have quoted. Yeah, I was about to say it. If you have higher rank lattice, then you have vanishing of cohomology for a large class of Banach spaces below the rank. And this class of Banach spaces includes all LPX. Just recently, we proved it for L2 spaces. That's this theorem with Roman Sauer. And this really, the proof that we had back then, uses the theory, cohomology theory of irreducible Banach unitary representations by Vaughan Zuckerman and Borel-Wallach, and it was very delicate. And now we have more Banach theoretic approach, more cohomological approach somehow. So I see this as an advance. And maybe I should also make a remark.
Sorry, and gamma is what in your theorem here? This conjecture is true. So, sorry.
Yes, fair enough, fair enough. Gamma lattice in simple Lie group or periodic. Well, it's, I mean, for rank 1, this is a trivial result. It holds, but it's nice to state it like this. And what I wanted to say here is maybe, where is it? I mentioned this result with Fuhrmann-Gelander-Monod, that the usual property T, vanishing of cohomology, of H1 is the same for L2 and for LP for P less than 2. Here, unclear if P equals 2, vanishing for P equals 2 implies vanishing of P equals 1, for example. Okay, I will not write all the words. It's unclear, and this is important because now I want to, I said at the beginning that it's still there. I wanted to talk about higher fixed points, and actually I prepared a proof using spectral sequences, etc. I will definitely not get there, but I want to relate the analytic part. In the example up there, I said that property T is an analytic thing, cohomological thing, with Banach space coefficients, hence analytic. And you have property Fa, which is a geometric property. And I want now to relate the two for higher property T. So it is not correct that higher property T with unitary coefficients implies fixed point properties, or we don't know it. But the L1 coefficients, which I emphasized already, do it. So let me state another theorem. Use this board. I'll use that board. General gamma or G. So not necessarily a higher rank lattice. If for every L1x with no fixed point, HK, and this is V. If you have the analog of higher property N, higher property T sub N, but instead of taking unitary representation, I'm taking L1 representations here. In fact, it's enough to take permutational L1 representation. Definitely, this implies by big L1. Then every action, then then you have Fa sub n. I will not write it down. This is a property defined by Benson-Farb. It is a generalization of the fixed point property for actions on tree. I will write down the definition. I didn't write what I just said. So Benson-Farb proved it in some cases, and he conjectured this theorem that he conjectured the conclusion of this theorem that I'm stating now. So then FAN, that is every action, every cellular action of gamma on a cell complex. So adjectives. He used the term cat 0. I hope you know what it is. I'll make a little correction in a minute. On a cat 0 cell complex. So this includes 3 in dimension 1 of dimension n as a fixed point. So actually, this color here, actually we proved a bit more than property Fn. You can, cat 0 implies contractible. You can just assume contractible. And then what you get is a finite orbit. So what is written on the board is the, and then omit this, that higher rank vanishing, or higher T, the L1 version, implies fixed point property for actions on cell complexes. So this is a new theorem, and this implies now lattices lattices have Fa rank -1. So this is Farb's conjecture. And this is just a combination of this statement here and this theorem over here. And again, I prepared a proof for this, but I will not be there. My time is almost up. And I realized that I even didn't get to discuss Gromov's conjecture, which also follows from that. If you care, you can ask about it. I think I will not go over time. So thank you.
Are there any questions?
What is Gromov conjecture?
Thank you.
I'll state Gromov's conjecture. It concerns LP cohomology. So a group always acts on itself, and I can take the space cohomology associated with this and LP complete it for any given P. This turns out to be equivalent to the following. Conjecture about HK of gamma on the completed group algebra. So the conjecture is for lattices, this is 0 below the rank. And now this now follows from our proof. It is Hausdorff at the rank again, it follows from our proof. I didn't state it this way, but and not vanish, does not. For p large enough, and again it vanishes above the rank for p large enough. I think this is not part of Gromov's conjecture, but this is these two facts are correct, and this is by Bader and Remy, following to a great extent the work of Pierre Pinceau and others, Yves Le Cornoulier, on the topic. So let me now, this theorem now is fully proven. This conjecture is fully proven. So let me just again state it. If I have a lattice in a simple Lie group or simple p-adic group, and I'm looking at the LP cohomology, when p goes to infinity somehow, it behaves as it should. I said that there is this unclear behavior for some groups. The vanishing rank of cohomology and the algebraic rank are not the same. But when p goes to infinity, it clarifies the matter. And maybe in some sense, unitary representation are not the right observer of this phenomena. What really happens, it happens at L infinity and when you approximate it. And in L1, when you approximate it, we have different phenomena, pre-dual phenomena. So again, the LP cohomology really sees the rank. It vanishes below the rank, as property Tn predicts, and it vanishes above the rank, even though the cohomological dimension is not the rank. The LP dimension somehow sees it, and at the rank we have very precise behavior, and it does not vanish in particular for p large enough. And I should say that the unitary representation theory has lots of appeal and many techniques that are not available for Banach space theories. For example, I didn't say it, I didn't get to do this, but when I look at the L2, LP equals 2 here, I have tools, for example, I have L2 cohomology and 4 Neumann dimensions, and very sophisticated tools that actually see the cohomology and measures it, but they are not available for higher P. I mean, one can prove that, I think there is a theorem by Monod and Peterson showing that there cannot be LP cohomological dimension. Nevertheless, we have this beautiful picture here that Gromov foreseen. And maybe just one last remark about this picture. In the p-adic case, whatever written here for p large enough actually is correct for every p. So for the p-adics, the cohomology theory doesn't care about p. You don't need to go to infinity in order to see the true phenomena. And in Lie theory, the cohomological dimension, the symmetric space behaves like a building maybe up to the rank. And then you have some cohomological dimension, complicated cohomological phenomena that are there in higher degrees, but they vanish when you look for infinity. From infinity, you get the asymptotic cone is a building of the right dimension, and if you take p to infinity, you actually see there, and then you behave more and more like a p-adic group. Okay.
So L infinity is excluded or not in your?
It's excluded, yes.
Some of the statements are not true, and some of the statements we don't know how to prove.
Okay. Of course, it is much bigger. It's not separable, so it's.
Yeah. So somehow, if you want to approach L infinity, maybe you don't want to think of it as a Banach space, but as a topological vector space with the weak star topology. And then this is a 4 Neumann algebra, and you really want to hold the cohomology with coefficients in a von Neumann algebra. This has lots of, if we had this, it had lots of other applications. We don't have it. We have an approximation. L1 is the predul of this von Neumann algebra. And also, we can say something about cohomology of preduls of von Neumann algebras in general. But this is... Yeah.
And what about lattices in non-simple higher rank, but of course which are not products of things in the factor, so can one have results from that?
Yes, yes. I choose not to focus on this, not to complicate my talk, but what we have, I think we have a rather satisfactory theory now for general irreducible lattices in products, so they are not living in factors. Otherwise, the theory of if just breaks to a product theory. They behave really. I mean, what we know is that the vanishing properties are the same as of the Lie group. So actually, okay, maybe I'll write it down. We have the following. So now this is semi-simple group, and I know now that HK gamma V, let me take V a G-rep. And I can look at HKGV and restrict to HK gamma V. And this is below the rank. This is an isomorphism. And actually, I used this when I discussed SLNZ at some point. I mentioned something of this sort for the trivial representation. So you should not expect vanishing here because you have cohomology coming from the factors. But this is really the only obstruction.
All right, maybe any more questions we can ask during the break. Let's thank you again.